morning, students. Welcome back to the class. Today we see some problems on complex numbers in which there are the problems of geometrical applications of complex numbers. So complex numbers 14th part. Complex numbers part 14. Here is the very first problem. If omega is a complex cube root of unity, complex cube root of unity, then find sine of omega to the power of 10 plus omega to the power of 23 into pi minus pi by 4. Here is the solution. Simplifying this expression, since omega cube is equals to 1, therefore omega to the power of 10 is equals to omega cube whole cube into omega, which is equals to omega. Omega to the power of 23 is equals to omega cube whole to the power of 7 into omega square, which is omega square. Therefore, omega to the power of 10 plus omega to the power of 23 is equals to omega plus omega square. Again 1 plus omega square is equals to 0. Therefore, omega to the power of 10 plus omega to the power of 23 is equals to omega plus omega square, which is equals to minus 1. Therefore, sine of omega to the power of 10 plus omega to the power of 23 into pi minus pi by 4. This is equals to sine of minus pi by 4. This is equals to sine of minus 5 pi by 4. Sine of minus theta is minus sine theta. So minus sine of 5 pi by 4. This is equals to minus sine of 5 pi by 4, which is pi plus pi by 4. This is equals to sine pi by 4, which is equals to 1 by root 2. Next, second problem. Second problem. If x square plus x plus 1 is equals to 0, then find the value of x plus 1 by x whole square plus x square plus 1 by x square whole square plus dash dash plus x to the power of 27 plus 1 by x to the power of 27 whole square. Here is the solution. Since x square plus x plus 1 equal to 0, put x is equals to omega r omega square consider here omega to the power of 3n is equals to 1, omega to the power of 3n plus 1 is equals to omega to the power of 3n plus 2 is equals to omega square. So consider x plus 1 by x whole square plus x square plus 1 by x square whole square plus x cube plus 1 by x cube whole square plus dash dash plus x to the power of 27 plus 1 by x to the power of 27 whole square. So this is equals to omega plus 1 by omega whole square plus omega square plus 1 by omega square whole square plus omega cube plus 1 by omega cube whole square plus dash dash plus omega to the power of 27 plus 1 by omega to the power of 27 whole square. So this is equals to 1 plus 4 into 9, which is equals to 54. Next, third problem. Third problem. If alpha is a non-real root of x to the power of 6 minus 1 is equals to 0, then find alpha to the power of 5 plus alpha cube plus alpha plus 1 whole by alpha square plus 1. Solution. X is equals to alpha, x to the power of 6 minus 1 is equals to 0. This implies alpha to the power of 6 minus 1 is equals to 0. Therefore, alpha to the power of 6 minus 1 is equals to alpha minus 1 into alpha to the power of 5 plus alpha to the power of 4 plus alpha cube plus alpha square plus alpha plus 1. This is equals to 0. So here alpha minus 1 is not equal to 0. This implies alpha to the power of 5 plus alpha to the power of 4 plus alpha cube plus alpha square plus alpha plus 1 is equals to 0. This implies alpha to the power of 5 plus alpha cube plus alpha plus 1 is equals to minus of alpha to the power of 4 plus alpha square. This is equals to alpha square is common, so alpha square plus 1. This implies alpha to the power of 5 plus alpha cube plus alpha plus 1 by alpha square plus 1 is equals to minus alpha square. Next, fourth problem. Fourth problem. If xn is equals to cos of pi by 4 to the power of n plus I into sin of pi by 4 to the power of n, then find x1 into x2 into x3 into dash dash up to infinite terms. Solution: xn is equals to cos pi by 4 to the power of n plus I sin of pi by 4 to the power of n for n is equals to 1, 2, 3 dash dash. Therefore, xn is equals to cis of pi by 4 to the power of n. Consider pi xn, n is equals to 1 to infinite, is equals to pi, the product cis pi by 4 to the power of n, n is equals to 1 to infinite. Since cis theta 1 into cis theta 2 dash dash cis theta n is equals to cis of theta 1 plus theta 2 plus dash dash plus theta n. Therefore, pi xn n equal to 1 to infinite is equals to cis of pi by 4 to 1 plus pi by 4 to the power of 2 plus dash dash plus pi by 4 to the power of n plus dash dash. So this is equals to cis of, here pi by 4 is common, so 1 plus 1 by 4 plus 1 by 4 square plus dash dash. So this is a geometric progression with common ratio 1 by 4. This is equals to cis of pi by 4 into 1 by 1 minus 1 by 4. This is equals to cis of pi by 4 into 1 by 1 minus 1 by 4, which is 3 by 4. 4 get cancelled. So this is equals to cis of pi by 3, which is cis of 60 degrees. This is equals to cos 60 degrees plus I into sin 60 degrees. Cos 60 is 1 by 2 plus I into sin 60 is root 3 by 2. This is equals to 1 plus root 3I whole by 2. Next, fifth problem. If z is equals to cos theta plus I sin theta, then find z to the power of 2n minus 1 by z to the power of 2n plus 1. Since cos theta plus I sin theta whole power n is equals to cis of n theta, which is called de Moivre's theorem. So consider z to the power of 2n minus 1 by z to the power of 2n plus 1. This is equals to 1 minus 1 by z to the power of 2n whole by 1 plus 1 by z to the power of 2n. This is equals to 1 minus 1 by cos theta plus I sin theta whole power 2n whole by 1 plus 1 by cos theta plus I sin theta whole power 2n. This is equals to 1 minus 1 by cis of 2n theta by 1 plus 1 by cis of 2n theta. So this is equals to 1 minus 1 by e to the power of I 2n theta whole by 1 plus 1 by e to the power of I 2n theta. So Euler form z is e to the power of I theta. So this is equals to 1 minus e to the power of minus I 2n theta by 1 plus e to the power of minus I 2n theta. This is equals to 1 minus of cos 2n theta minus I into sin 2n theta whole by 1 plus cos 2n theta minus I sin 2n theta. So this is equals to 1 minus cos 2n theta minus of minus, which is plus I sin 2n theta whole by 1 plus cos 2n theta minus I into sin 2n theta. This is equals to 1 minus cos 2n theta is 2 sin square n theta plus I into sin 2n theta is 2 sin n theta into cos n theta whole by 1 plus cos 2n theta, which is 2 cos square n theta minus I into sin 2n theta, which is 2 sin n theta into cos n theta. So this is equals to, in the numerator, 2 sin n theta is common, so sin 2n theta, sin n theta plus I into cos n theta whole by, in the denominator, 2 cos n theta is common, 2 cos n theta is common, so cos n theta minus I into sin n theta, 2 to get cancelled. So this is equals to tan n theta into here we can place 1 in terms of I, which is minus I square, I into cos n theta whole by cos n theta minus I sin n theta. This is equals to, here I is common, so I into tan n theta into cos n theta minus I sin n theta whole by cos n theta minus I sin n theta. These two get cancelled. This is equals to I into tan n theta. Next, sixth problem. If mod z plus z bar plus mod z minus z bar is equals to 2, then z lies on, here z is a complex number, let z is equals to x plus iy. This implies z bar is equals to x minus iy. Consider mod z plus z bar plus mod z minus z bar is equals to 2. So this implies z plus z bar is 2. So 2 mod x plus this is z minus z bar, which is 2 mod iy, which is equals to 2. So 2 get cancelled. This implies mod x plus mod y is equals to 1. This implies plus or minus x plus or minus y is equals to 1. Therefore, z lies on square. There are 4 equations. So x plus y is equals to 1, x minus y is equals to 1, minus x plus y is equals to 1, minus x minus y is equals to 1. So therefore, x plus y is equals to 1, x minus y is equals to 1, and minus x plus y is equals to 1, minus x minus y is equals to 1. So all these equations form a square. So which implies form a square. Therefore, z lies on square. Next, 7th problem. If the equation mod z minus z1 whole square plus mod z minus z2 whole square is equals to k, represents the circle, represent the equation of the circle, equation of a circle where z1 is equals to 2 plus 3i, z2 is equals to 4 plus 3i, are the endpoints of a diameter, then find k value. Here it is a standard formula. The answer is very simple. K is equals to mod z1 minus z2 whole square. Here z1 is equals to 2 plus 3i, z2 is equals to 4 plus 3i. So this implies k is equals to 4. K is equals to 4. Next, 8th problem. Eighth problem. The number of common solutions are roots of the equations x cube minus 1 is equals to 0 and x power 6 minus 1 is equals to 0 is solution. Common solution, the number of common solutions. So the number of common solutions are roots is GCD of 3, 6, which is equals to 3. 3 2s are 6, 0. So 3. Next, ninth problem. Ninth problem. If 2 cos alpha is equals to x plus 1 by x and 2 cos beta is equals to y plus 1 by y, then find x to the power of 10 by y to the power of 12 minus y to the power of 12 by x to the power of 10. Solution. Let x is equals to e to the power of I alpha, y is equals to e to the power of I beta. Therefore, x to the power of 10 by y to the power of 12 minus y to the power of 12 by x to the power of 10 is equals to e to the power of I 10 alpha whole by e to the power of I 12 beta minus e to the power of I 12 beta by e to the power of I 10 alpha. So this is equals to e to the power of I 10 alpha minus 12 beta minus e to the power of I into 12 beta minus 10 alpha. This is equals to e to the power of I into 10 alpha minus 12 beta minus e to the power of minus I into 10 alpha minus 12 beta, which is equals to 2I sine of 10 alpha minus 12 beta. Next, 10th problem. 10th problem. The area of the triangle, with vertices z comma iz comma z plus iz is 50, then find mod z. Solution. The area of the triangle with vertices z iz z plus iz is 1/2 mod z square, which is equals to 50. This is given. So this implies mod z square is equals to 100. This implies mod z is equals to 10. Next, 11th problem. Find the sum of the series. Find the sum of the series sin alpha plus x into sin of alpha plus beta plus x square by 2 factorial sin of alpha plus 2 beta plus dash dash. Here is the solution. This expression is in terms of sign. So let S is equals to sin alpha plus x into sin of alpha plus beta plus x square by 2 factorial sin of alpha plus 2 beta plus dash dash. Therefore, C is equals to cos alpha plus x into cos of alpha plus beta plus x square by 2 factorial cos of alpha plus 2 beta plus dash dash. So introducing the cos series. Therefore, C plus IS is equals to IS. So cos alpha plus I sin alpha plus x into cos of alpha plus beta plus I into sin of alpha plus beta plus x square by 2 factorial cos of alpha plus 2 beta plus I into sin of alpha plus 2 beta plus dash dash. So this is equals to e to the power of I alpha plus x into e to the power of I alpha plus beta plus x square by 2 factorial into e to the power of I into alpha plus 2 beta plus dash dash. In this series, e to the power of I alpha is common. E to the power of I alpha is common. So e to the power of I alpha is common. So 1 plus x into e to the power of I beta plus x square by 2 factorial e to the power of I 2 beta plus x cube by 3 factorial e to the power of I 3 beta plus dash dash. So this is equals to e to the power of I alpha into 1 plus x into e to the power of I beta whole power 1 by 1 factorial plus x into e to the power of I beta whole square by 2 factorial plus x into e to the power of I beta whole cube by 3 factorial plus dash dash. So now this is an exponential series. This is now an exponential series. So this is equals to e to the power of I alpha into e to the power of I into e to the power of x into e to the power of is equals to e to the power of I alpha into e to the power of x into I beta e to the power of x into e to the power of x into e to the power of I beta. So this is equals to e to the power of I alpha into e to the power of x into e to the power of I beta is cos beta plus I sin beta. So this is equals to e to the power of I alpha plus x into cos beta plus I sin beta. This is equals to e to the power of x cos beta plus I is common, alpha plus x into sine beta. This is equals to e to the power of x cos beta into e to the power of I into alpha plus x sin beta. So C plus IS is equals to e to the power of x into cos this is cos beta into cos of plus I into sin of x plus sin of alpha plus x sin beta. So this is equals to e to the power of x cos beta into cos of alpha plus x sin beta plus I into e to the power of x cos beta into sin of alpha plus x into sin beta. So equating the imaginary parts on both sides. Therefore S is equals to e to the power of x into cos beta into sin of alpha plus x into sin beta. Next, 12th problem. So, 12th problem. If a1 of z1 comma a2 of z2 are the adjacent vertices of a regular polygon if imaginary part of z1 by real part of z1 is equals to 1 minus root 2, then find the number of sides of the polygon. solution. It is clear that origin is the center of the polygon. So clearly origin is the center of the polygon. Center of the polygon. Center of the polygon. Let Z1 is equals to R e to the power of I theta, and Z2 is equals to, and this implies Z1 bar is equals to R into e to the power of minus I theta. So here imaginary part and real part of Z1, and therefore imaginary part of Z1 is equals to R sin theta. Real part of Z1, real part of, this is imaginary part of Z1 bar. Z1 bar. So imaginary part of Z1 bar is minus R sin theta. Real part of Z1 is equals to R cos theta. R cos theta. Therefore, consider imaginary part of Z1 bar by real part of Z1 is equals to minus R sin theta by R cos theta, which is minus tan theta. This is given as 1 minus root 2. This implies tan theta is equals to root 2 minus 1. Therefore, theta is equals to pi by 8. Tan theta is equals to root 2 minus 1. This implies theta is equals to pi by 8. If n be the number of sides of polygon, then pi by n is equals to pi by 8. This implies n is equals to 8. So these are the problems that are covered in this class. So far we have seen 14 classes to complete this complex numbers with a clear point of view. So you follow up the videos what we were posted in the YouTube. Thank you.